Can you see my slide and can you hear me?
I can hear you. I can see what looks like you haven't put your slide in presentation mode.
Wait a second. Yes, my slide is just a minute. Hold on a second. Okay. Is that working? Can you see that? No? Okay. Let me try this again. We had this problem.
It looks
Try
just
come-
like a document.
Yeah. All right. So I'll go back just a second. Hold on a second. We're going to close that. We're going to reopen it. Excuse me. Please bear with me. Okay. So now let's go to Zoom and let's share my screen. Bildschirm freigeben. Okay. So can you see that? Okay, wait a second.
Yes.
Yes,
And is it in full screen mode now?
it is not yet. No.
It is not yet. Is it switching between slides? Great. We're having the same problem we had yesterday. Bringen Sie Ihre freigegebenen Fenster in den Vordergrund. Okay, let's do that. Did that help? No. I'm sorry. Excuse me, Steve. I am not doing a good job here. Let's try one more thing. I'm going to quit.
It looks like you had a PDF document open.
I
It's a
had
PDF.
But it should go into the full screen mode. And it
You
did a
know,
minute.
if you keep it in the PDF and you can just step through the
Yeah,
pages.
well, we might just have to do that. All
Yeah,
right.
that, I mean,
Hold on a
it
second.
was
Let's try
all
it.
quite
Okay.
legible.
Okay, try one more time. Fenster auswählen, Shift halten, um mehrere Fenster. No. Okay, Ton freigeben. Yes. For video clip. Okay, so no, abbrechen. And okay, can you see anything?
Yes, and it's a PDF document, so just
Okay,
go through the pages.
Is it now in presentation mode?
It is not,
Well, great. Okay, we're just gonna have to work like this. I'm sorry.
and it'll be fine.
Well, it's not fine, but we'll just go like that. All right, so thank you. I'm gonna count that as my start. Origin of life of origin of microbes. Thank you very much for the invitation to be here. The origin of life is a highly debatable topic because it hinges upon what definitions we have for life. The origin of microbes is not so readily debatable because microbes are very well defined. They grow all by themselves, given water and proper substrates, and they have a physiology. So there are tomes of literature on the definition of life, and there are no tomes of literature on the definition of microbes because they are very well defined. So yesterday we heard something from Emmanuel. We don't know anything about the metabolism of LUCA. Well, I'd like to disagree, actually. We know quite a lot. And here are some of the papers that the group has been producing recently where we're learning something about the core physiological reactions, the core metabolic reactions at the of physiology that provides carbon and energy and nitrogen and bases and amino acids and cofactors in the physiology of ancient cells. These are some of the people who've been doing that work. We've got Martina Preiner and Felipe Sousa and Joanna Xavier. They've moved on to Utrecht, Vienna, and UCL. Felipe just got her tenure in Vienna recently. Congratulations, Felipe. Still in Düsseldorf, we have Max Probander, Andre Vera, and Jessica Wimmer. You see how they're smiling because they're still in Düsseldorf, and those who are not in Düsseldorf are not smiling so much anymore. There's Joseph Moran, our partners that we definitely need to mention. Joseph had a wonderful paper on TCA cycle intermediates and synthesis of amino acids from those intermediates using hydroxylamine to get glycine, alanine, glutamate, and aspartate from the corresponding 2-oxo acids. That was Nature 2019, relates to the discussion on synthesis of amino acids. And Harun Tusuz, who's been providing us with some wonderful catalysts. He's at the Max Planck Institute for Coal Research, or Kohleforschung in Mülheim. And the reason that he's smiling is that right down the hall from him is where the Nobel Prize for Chemistry landed this year in the Abteilung List. And so the Max Planck Institute in Mülheim has a lot to celebrate right now. Life is a chemical reaction, and we're concerned in my group with what was the chemical reaction from which it started. Life is not just the reorganization, rearrangement of pre-existing components. It is an energy-releasing reaction that assembles those components by itself during the course of energy release. That's different from delivery scenarios where we do the synthesis in space and then reorganize on Earth. We think that if we look at life as a chemical reaction, we should be looking for a chemical reaction that releases energy and can do some synthesis at the same time. The idea of autotrophic origins of life from CO2 is not new. This is a picture from Konstantin Merezhkovsky in 1910. And if you see at the bottom, he's got something called Biococcus, and these are just little things, hypothetical organisms living at the in hot conditions, basically inorganic components. If we look at what he was talking about, he was saying that the very first cells had a minimal size. They were too small to be seen by the microscope. They had no organization. That was his way of saying that they were prokaryotes, not eukaryotes. They had the ability to live at very high temperatures, close to the boiling point. They had the ability to live without oxygen. They had the ability to synthesize proteins and carbohydrates without the help of chlorophyll from inorganic substances. Now that is chemolithoautotrophic origins, we call it today. It's 1910. And they were also highly resistant to alkali and high salt concentrations and sulfur and poisons. So the idea of autotrophic origins and extremophilic origins, these are conditions that are very similar to hydrothermal vents, is quite old. The kind of hydrothermal vents that we think are interesting for the origin of life were postulated by Mike Russell in his expeditions on looking for ore deposit sites, and they were discovered by Deb Kelly at Lost City, discovered in 2000. And the interesting thing about Lost City from a microbiological standpoint is that the effluent from that hydrothermal system contains a lot of hydrogen, about 10 millimolar hydrogen, which is orders of magnitude more than microbes need to live. They form bubble-like microcompartments, which is what Mike had in mind when he found this rock here at the silver mines in Ireland in the 1990s. And this is a picture from one of Mike's most famous papers. This is Russell and Hall, 1997, showing a botryoid, a fossilized hydrothermal vent that has a chimney at the arrow. It's about the size of a laser pointer, and little bubbles down at the lower left. Those are called botryoids. And when Mike cut those open, well, they're hollow inside and made of inorganic compartments. Now, these are interesting structures because they provide a concentration mechanism. Regardless of what chemistry we assume at the origin of life, there had to be some concentration mechanism in order for these compounds to react and attain higher complexity, and these inorganically forming microcompartments perform that function. Another function that the microcompartments serve in today's presentation in the theory that we're talking about here is that they're made of transition metal sulfides. Now, transition metals, for the chemists among you, we don't need to say that they have a special property. They have d electrons, and these d electrons can form metastable bonds with carbon and nitrogen so that the latter can react with hydrogen or with oxygen atoms or with other carbon or nitrogen atoms, so that a reaction takes place on the activated compound. It leaves then the transition metal, the d electron orbital is pulled back in, and the metal leaves the reaction unchanged, but the carbon and nitrogen can be changed. This is catalysis. And the property of catalysis is a property of the elements. We don't have to change them. We can modify that by coordination states, but the property of catalysis is a property of the elements. So we have catalytically walled compartments made out of catalytic compounds. So this is a picture of Lost City. Deb Kelly provided this picture, and you can see that over on the right, this is a section through part of the calcium magnesium carbonate structures. These are about 60 meters high, and Lost City is about 100,000 years old, excuse me. So these structures 60 meters high with a very intricate compartmentation systems are naturally forming, and that's an analog for what we think might have been going on 4 billion years ago. The model has it that hydrogen and CO2 are the original redox couple giving rise to reduced carbon compounds, and that's because in the reaction of hydrogen with CO2, the equilibrium lies on the side of reduced carbon compounds, and that can get us to thioesters, amino acids, sugar bases, inorganic precursors, and something like an RNA world, but not in a free-living cell, rather in a higher level of organization within the catalytically walled compartments that gave rise to the substances themselves that were reacting further to give rise to the non-free living universal common ancestor. Of course, the iron sulfur clusters in modern proteins are not inventions of the biological world. In this case, they are simply ways that in which proteins learn to incorporate these catalysts into their structure so that they became portable and genetically specifiable. In the as the compartments of the contents of these compartments became more complex, there was differentiation into the bacteria and the archaea. And the final split had to do with the origin of lipid membranes, the isoprene ethers of the archaea and the fatty acid esters of the bacteria, the stereochemistry of glycerol phosphate being different between the two, and peptidoglycan in the bacteria and S layer in the archaea, so that these two could emerge independently. That's the model. So where is the energy coming from to drive all this, right? This is the problem with all of the origin of life theories. We have to have energy. The energy is coming from process of serpentinization in this theory. And that is, as Steve nicely explained, it's an exergonic and energy releasing process that takes place within the Earth's crust, where water reacts with iron magnesium silicates to give rise to serpentinite, and hydrogen as a byproduct. I think a cubic meter of olivine gives rise to about 12 cubic meters of hydrogen during the serpentinization process. And furthermore, it's exergonic and can't be stopped. It's been going on since there was water on Earth. This is where our energy is coming from. This is the rock, and the energy is directly relates to microbial physiology, because acetogens and methanogens grow from the reaction of hydrogen with CO2. All right, so the acetogenic reaction is exergonic, giving rise to acetate from H2 and CO2. Methanogenesis slightly more exergonic because the product is more reduced, and to gas, and even to the level of the energy-rich thioester, the energy is an exergon. The reaction is exergonic. So that's a good source of energy. And so we know where the H2 is coming from. It's coming from serpentinization. Where is the CO2 coming from? And this is where Steve really set the stage. The moon forming impact melted the Earth. It was a ball of boiling magma, 2,000 degrees, 1,500 degrees. And that means that all the carbon basically on the planet was transferred to the gas phase as CO2. So we had CO2 in the atmosphere, water in the atmosphere from the moon forming impact. The Earth cools, it rains, we get deep oceans, CO2 starts to re-enter the aqueous phase and then is drawn down into cracks in the crust through serpentinization, where hydrogen is being made through the serpentinization process, and there we get organic reactions. So these are the pathways that the organisms use, the acetogens and methanogens. They differ, but their chemistry is the same, in that we get a transition from CO2 down to methane or to acetate. Now, the core of this reaction is shown right here in a slide from a paper by Steve Ragsdale. It's the mechanism. And one of the curious things that people have looked at is the CO2 reduction has been very difficult actually to perform in the laboratory. And looking at this a few years ago, I said to myself, This is actually native metal in the active state of the CODH reaction. That is the reaction that gives rise to carbon monoxide with electrons from ferredoxin. That's that nickel zero at the lower right. And I said, CO2 reduction in biology is always a 2-electron reaction. And maybe that's why people have not had great success using iron sulfur minerals, because they are always, there's always 1-electron reactions. So we started to try this with Martina Preiner, who came to Dusseldorf from Munich to do her PhD thesis. And we found some cooperation partners who were willing to work with us, Harun Tusuz at MP Mulheim, Chris Greenwell in Durham, and Joe Moran in Strasbourg. So we started working with auerite, a natural native metal that's made it's ubiquitous in serpentinizing systems. And we were able to get some nanoparticular auerite from Harun in Mulheim, and we found that it would synthesize some CO just from CO2 and water. And then when we started to add hydrogen, and this was Martina's discovery, just emulating the microbial pathway, down at the bottom, you see CO2 and H2, 100 degrees, auerite and water. We were getting acetate, formate, ethanol, pyruvate, and methane. This is the backbone of microbial physiology in organisms that use the acetyl-CoA pathway. It's unfolding in front of our eyes overnight and very specifically. So that's the reaction. That's the reactor. H2CO2 water in the presence of auerite, 16 hours, 100 degrees, formate, acetate, pyruvate, and methane. And this is these are all the only compound that is not an immediate an intermediate in the acetyl-CoA pathway is methanol. We're not just getting these compounds among others. These are the main compounds we get. This reaction generates is a phenocopy of the acetyl-CoA pathway. It's actually amazing. So that's been published. Here's the pathway drawn by Georg Fuchs, CO2 to formate, formyl, methylenyl, methylene, methyl, off to methane, acetate, and pyruvate. And these are the products that we get from this reaction using either greigite, magnetite, or auerite. And auerite gives us the best similarity to the biological pathway. So we think that's very good. That shows that there's a nice correlation between these natural reactions of H2 and CO2 on a hydrothermal mineral and microbial physiology. This is just to show that these compounds are actually catalysts. They're not reacting, they're catalytic. That's the pathway that we get. I'm going to have to shorten this talk. That fits very well with our genetically inferred last universal common ancestor that we published a few years ago, the physiology of the last universal common ancestor, acetyl-CoA pathway living off of geochemically synthesized methyl groups, and we can get those methyl groups in the laboratory. Two more slides.
Now would be a good time to wrap up.
Okay, 2 more slides. We're not going to do the movie. So life is a chemical reaction, an exergonic one. From which reaction did it start? It started from serpentinization. These are the people who are doing the work. They're all smiling because we still have a fair amount of luck publishing papers. And this is the group and the people that gave us the money, the Volkswagen Stiftung, the Clue Foundation, the ERC 3 times. Thank you very much, everybody involved with the ERC, Moore Simons, DFG, and I'll be glad to take any questions if you have them.